Introduction. In the field of inorganic chemistry, color is commonly associated with DD transition. If this in case, why is that some transition metal complex show intense color in the solution but possesses no d electrons? In transition metal complex, a charge in the electron distribution between the metal and the ligand gives rise to a charge transfer bonds when performing U visible spectroscopy experiments. For complete understanding, a brief introduction to electron transfer reactions and the Mercator's hash theory is necessary. Outer sphere charge transfer reactions. Electron transfer reactions fall into two categories, that is, inner sphere mechanisms and outer sphere mechanisms. Inner sphere mechanism, electron transfer occurs via the covalent bonded bridging ligand. Outer sphere mechanisms. Electron transfer occurs without a covalent linkage forming between reactions. Here the reactions. Here we focus on outer sphere mechanisms. In the self-exchange reactions, the reactant and the product side of the reactions are the same. No chemical reactions takes place and only an electron transfer is witnessed. This reductant oxidant pair involved in a charge transfer is called the Perkus complex. The Frank-Condon approximation states that the molecular electric transition occurs much faster than a molecular vibration. Here is some examples. Then a brief introduction to Mercator's hash theory. Mercator's hash theory relates kinetic and thermodynamic data for the two self-exchange reactions with data for the cross reactions between two self-exchange partners. This theory determines whether an outer sphere mechanism has taken place. This theory is illustrated in the following reactions, that is self-exchange and cross reactions, etc. The Gibbs free energy of activation delta G is represented by the following equation. Here the abbreviations for T. T is temperature in Kelvin, R is molar gas constant, K is Boltzmann constant, H is Planck's constant, and so on. If the outer sphere mechanisms is taking place, the calculated values of K1 to K12 will match or agree with the experimental values. If these values do not agree, this would indicate that another mechanism is taking place. Then the Laproyd selection rules and weak DD transitions. DD transitions are forbidden by Laproyd selection rule. Laproyd selection rule, that is delta L, it is equals to plus or minus 1. Laproyd allow transitions. A charge is occurs, that is S to P and P to D. Laproyd forbidden transitions, the pretty remains exchanged, that is P to P and D to D. D to D transitions results in weak absorption bonds, and most D block metal complex display low intensity color in solutions, and D0 to D10 complexes. The low intensity color indicate that there is a low probability of DD transition occurring. Ultraviolet visible spectroscopy is the study of transitions involved in the rearrangement of valence electrons in the field of inorganic chemistry. UV or visible is usually associated with DD transitions and color transition metal complex. The color of transition metal complex solution is dependent on the metal. The metal oxidation states, then the charge transfer bonds. If color is dependent on DD transitions, why is that some transition metal complex are intensely colored and solutions but possesses no D electrons? Here the figure represents the different types of colors. Then ligand to metal and metal to ligand charge transfer bonds. Ligand possesses sigma, sigma star, pi, pi star, and non-bonding molecular orbitals. If the ligand molecular orbitals are full charge, the transfer may occur from the ligand molecular orbitals to the empty or partially filled metal d orbitals. The absorptions that arise from the processes are called ligand to metal charge transfer bonds, that is LMCT. LNCT transitions results in the intense bonds. Forbidden DD transitions rising to the weak absorption transfer results in the reduction. If the metal is in the low oxidation states and the ligand possesses low laying empty orbitals, then the metal to ligand charge transfer, that is MLCT transitions, may occur. LNCT transitions are common for coordination compounds having pi acceptor ligands. Upon the absorption of ligands, electrons in the metal orbitals are excited to the ligand pi star orbitals. Then effect of solvent polarity on CT spectra. This effect only occurs in the species being studied in an ion pair. The positions of CT band is reported as transition energy and depends on the solvating ability of the solvent. A shift to lower wavelength is observed when the solvent has high solvating ability. Polar solvent molecules align their dipole moments maximally or perpendicularly with the ground state or excited state dipoles. If the ground state or excited state is polar, and interactions will occur that will lower the energy of the ground state or excited state by solvation. This effect of solvent polarity on CT spectra is illustrated on the following examples. Then consider you're preparing a sample of UV or visible experiments and you decide to use a polar solvent. Is the shift in the wavelength observed when both the ground state and the excited state are neutral? When the both ground state and the excited state are neutral, a shift in wavelength is not observed. No charge occurs. Link dissolves like a polar solvent would not be able to align its dipole with the neutral ground and excited state. The excited state is polar, but the ground state is neutral. Then the excited state is polar, but the ground state is neutral. The solvent only interact when the excited state. It will align its dipole, the excited state, and the lower is lower energy by the solvation. These interactions will the lower the energy to the polar excited state, then decrease the frequency, increase wavelength. Then the ground state and excited state is polar. If the ground state is polar, the polar solvents will align its dipole with the ground state. Maximum interactions will occur and the energy of the ground state will be lower. That is increased wavelength, lower frequency, and lower energy. The dipole moment of the excited state would be perpendicular to the dipole moment of the ground state. Since the polar solvent dipole moment is aligned with the ground state, these interactions will raise the energy of a polar excited state. That is decrease in wavelength, increase in frequency, and increase in energy. Then the ground state is polar and the excited state is neutral. If the ground state is polar, the polar solvents will align its dipole with the ground state. Maximum interactions will occur, the energy of the ground state will be lowered. That is increase in wavelength, lower frequency, and the lower energy. If the excited state is neutral, no charge in energy will occur. Like dissolves like and polar solvents won't be able to align its dipole with the neutral excited state. Overall, you could expect an increase in energy illustrated below. Then how to identify charge transfer bands? CT absorptions or the selections rules allowed the results intense. These values are given here. A very intense, that is have a large extension coefficient, or normally broad. Display very strong absorptions that go above the absorptions scale. Then ligand to metal charge transfer. KMnO4 dissolves in water, gives instant CT bond. The one LMCT bond is the visible in absorbed around 530 nanometer. The bonds of 580 nanometer gives rise to the deep purple color of the solution. An electron from the oxygen lone pair character orbitals is transferred to an low-lying Mn orbital. Here is the graph representation. Then metal to ligand transfer. That's all given below. This is my representation.